Section 6.4, the Gibbs energy of a reaction mixture. For a chemical reaction that contains species 1, 2, 3, etc., the Gibbs energy of the total reaction mixture depends not only on temperature, pressure, but also on the changing number of moles of every single species. Therefore, G is a function of T, P, N1, N2, N3, etc. Therefore, dG depends on dt, dP, and then dN1, dN2, dN3. Over here, if we look at how G depends on temperature, we need to hold all other variables constant. If we want to look at how G depends on pressure, we need to hold temperature and the number of moles of all species constant. Also, G depends on N1, the number of moles of species 1. In this case, we need to hold temperature and pressure, and also N2, N3 constant. Over here, this is dN2. We need to hold Tp, N1, N3 constant. Same here. So we define a new concept, so-called chemical potential. Mu1 in here is delta G over delta N1 when we hold Tp, N2, N3 constant. And similarly, mu2 is delta G over delta N2. So in general, mu sub I for species I is delta G over delta N sub I when we hold temperature, pressure, and the amount of all other chemicals constant. And then the equation becomes a little shorter. dG is delta G over delta T times dt, delta G over delta P times dP, and then we have the sum here. It's mu I times dNi. Again, mu I is the chemical potential of species I. Well, if you have only one species, this mu sub I is simply the molar Gibbs energy of that species. At constant temperature and pressure, so we sometimes do chemical reactions under the constant temperature and pressure condition, and then dG is simply the sum of mu I di. Now again, when there's only one pure substance B, so we have this equation under constant temperature and pressure, and now you can see mu sub B is dGB over dNB, and GB is simply the number of moles of B times the molar Gibbs energy, and we just proved this mu B is equal to the molar Gibbs energy of B. So if you have only one pure substance, the chemical potential is simply the molar Gibbs energy of that substance. But if you are looking at a mixture, for example, of two gases, this mu does not only depend on the molar Gibbs energy of that species, it also depends on the mole fraction of the species. Now let's look at the Upac definition. Again, this is Upac definition over here. All right. So mu is delta G over delta N for the species. For a pure substance, this asterisk stands for pure. So the chemical potential of pure B is simply the molar Gibbs energy of B. So that's very simple. Why is this delta G over delta N called the chemical potential? Well, just imagine this. Water flows from a higher potential energy region to a lower potential region, right? So chemicals always transport from a higher chemical potential region to a lower chemical potential region. So that's why it's called chemical potential. Remember the conditions for the natural direction. For an isolated system, we need to look at entropy. When temperature and pressure are constant, we need to look at G. G always decreases. If the temperature and volume is a constant, A always decreases. So it seems like we have different conditions, and then we have different criteria. However, if we use chemical potential, it's always true that chemicals transport or flow from a higher chemical potential region to a lower chemical potential region. It's always true. under whatever conditions. This statement is always true. Chemicals always transport from a higher chemical potential region to a lower chemical potential region.